Today we're going to talk about sensors, but just to give a little bit of a context about how sensors fit in for sustainability and sustainable steel industry. So we've heard a lot about sort of going through the supply chain, the recycling, and we've heard a little bit from Zhou about the importance of sensors for sorting and for quality control of the materials going in. We've heard quite a bit about, say, some of the metallurgy, and yesterday we heard Matt talking about how some of the modelling work allowed for putting in new compositions, new materials, and doing it the right first time, which I think is a fantastic example of how we can use digital twins and modelling to be able to get sustainability through reducing the scrap rates and being able to customize materials for given requirements. In order to be able to do all of these things, to develop the models, and we're going to hear later in today's session about, or later this morning, about digitalization and the importance of being able to do digitalization both in terms of material passports so that we can track materials and understand them, and in terms of things like digital twins so we can do that right first time. And in order to be able to do that, we need data, and we need accurate data that allows us to optimize models, to be able to have the material and product passports. That means that at end of, I'm going to call it end of first life, we can decide what we do. Because whilst recycling is really important, if we can also encourage reuse, remanufacturing, then from a sustainability of the steel sector, we improve things. And we have better control and knowledge of properties. And again, it comes back to information, quality of information. And some of that is by being able to customize the data through processing based on composition, put that into blockchain, be able to retain that data through life. And some of it is about having more data that is targeted to the things that we need to know. And for me, that's where the sensors fit in. And so sensors across the board are part of the picture to give us that richness of data, to make all of those aspects that contribute to sustainability in place. So we're going to hear a little bit about some specific sensor technologies, but really it's about sort of saying, well, what are the opportunities for increased data acquisition? And then really, I guess the second part is, well, what else do we need? And that's, we're going to talk about some of the sensors, but actually I want to put out a challenge to the audience is, well, from your perspective, what data is actually needed? And where do those of us who work in the sensing side of the research and development need to be thinking about so that we can provide the solutions to get that data that will contribute to that richer picture and make the whole sector more sustainable. And there are lots of activities that are going on internationally to be able to reach that point. So we'll hear a little bit about some of the sensors that can look at product and product performance, and that's really important because, as I mentioned, that at end of first life, we need to be able to make intelligent decisions about how we deal with that material in the next side of things. A lot of people now are looking at utilizing data even from existing sensors in products to be able to make that kind of selection at end of first life. It's a really, really important area. We'll hear some of the sensors that can contribute to understanding there. It's also about through process. So again, going back to Matt's talk and understanding their grain size and grain size development through hot working, then how do we do that? There's some really nice work that's being done in Swansea in Sweden, looking at using laser ultrasonics for real-time in-situ measurement of grain size during hot processing, which I think is fantastic in terms of being able to implement that, and that's gone into SSAB as a trial and getting some really nice information from that. And we'll hear a little bit about electromagnetic sensors for phase transformation, some of which are going into the Port Talbot mill, so just down the road, some of the state-of-the-art sensors that are going in, and it's only the second site that having those sensors in. So we'll hear a bit more about that, and I think that's really exciting. And it's then sort of saying, not just we're putting them in, but it's the exploitation. You know, how do we use that richness of data to improve things going forward? So again, really lots of examples. We're going to scratch the surface and give you a flavour for some of those that are there. But please bear in mind, it goes across the whole of the supply chain, the whole of the manufacturing sector. So please, can I invite our first speaker, Professor Tian, to come up and tell us a little bit about the sensors work that he's involved in.
Okay, good morning, everyone. Thanks, Claire, to organize this session. So I will talk about innovative electromagnetic non-destructive testing and evaluation for steel. My name is Tian from Newcastle. I try to be quick. I finish within 20 minutes. So basically, NDT and the structure-based monitoring probably is new for this community. I will talk about roughly what this is about. I talk about the RFID sensor we developed in Newcastle, and then how could we use this one for digital steel and the tracing and the tracking quality of steel. I will talk about different electromagnetic sensors for different applications, like stress pipeline application, and also talk about the metrology and the NDT merged together for future quality control. So, as I said, I'm from Newcastle University. We have one sensor, signal processing and the communication group. So I'm actually in charge of the sensor theme. So in the sensor theme, we develop different kind of sensor for non-destructive testing and the evaluation, also structures monitoring and the IoT for network monitoring. So after that, we develop instrumentation, develop modeling, and the system as well. So after that, we develop different applications, like you say, high-speed railway, wind turbine, and the steel manufacturing, and the oil and the gas, particularly for power plant. As you can see, most of the end use for mechanical object, I think steel in particular. So what is NDT is about? I think everyone here should be not different. I think if you go to hospital and have a check, so we have ultrasonic, we have X-ray, we have a different measurement and the diagnostic system. So it's very similar. NDT is similar like a measurement. Only one big difference, we have the excitation source. For example, X-ray, you have the X-ray source, you have ultrasonic, you have ultrasonic source there, and you also MRI, also you have the magnetic field and generate the different kind of excitation. So that means NDT, we have excitation. After that, we have a sensor, we have the signal processing, we also have the pattern or data processing and the decision making. So rest of them very similar to instrumentation and the measurement area. Structure-based monitoring actually extend NDT application just for permanent install sensor. So basically, we install sensor associated with different sample, different object, and the continued monitoring. We also could say use in situ monitoring. In this time, we are not only have a sensor, we also have the communication and send the data to the place we would like to use. So then in Newcastle, we have combined several different approaches together for NDT. So basically, we have the analytical modeling. We also have a numerical simulation and modeling as well. So after that, we design and develop different systems for different kind of the instrumentation system. So through experimental approach, we develop sensor and the monitoring system. So one of the example application, for example, in the walk-through at the airport, so we have the magnetic camera, and we also associate with different mechanical detector for walking through system. In this way, we can monitor any mechanical object. So this time, so we don't need you go through the walking through system at the airport, take out all the mechanical goods, mechanical sample. So what we can just detect and localize different kind of mechanical object and then make the right decision at the right time. So similar case, we can apply this one, for example, like a post-eddy current. So traditional eddy current just use single frequency to excitation. What we do different, we do pulse, because the pulse excitation, we can have the time and the frequency domain combined together. Then we can do the measurement without defect, and then with defect, and then we do differential signal to do the feature traction to do the measurement. So after that, we developed different post-eddy current sensor system at the Newcastle University. So we use this one for corrosion detection under coating. We also develop flexible eddy current film for different kind of the particular complex geometric application. And this one, as you can see, flexible coil film, we can measurement different kind of defects as a sensor array. So one of the interesting area I think could be audience maybe very interesting, RFID sensor recently we developed. So basically everyone here just know for steel material, we have a quite complex parameters there, physical, chemical, mechanical, or geometric information. So what we could do, we can develop different kind of sensor. One of the sensor, I think we use RFID. RFID, I think, is not new to everyone here. So you have a bank account, you have staff card. I think that's why you have two ports. One is a transponder, another one is a reader. So normally, the transponder, the card we hold, is a passive, no any power required. When we reach near the reader, and the reader coil will excite, inject energy to transponder, and then transponder wake up, get the power, and then we can use this kind of switch, get a different ID, and then we get the different identification and the communication, like near field communication. What we do different, we try to bring these two characters together with sensing. Then if we have sensing, because the transponder and the reader coil exactly the same as we use what we call inductance or eddy current. So if we extend that one, we could apply this one to measurement the steel property. And then we also can stick transponder with steel material or with sample when the tracing supply chain and the tracing manufacturing. So if we put it this way, we have a different application. So for example, we could use a metal material with just print and the coating on steel material or steel sample. We also can design different RFID sensor to do stress measurement. So one of our application in the Newcastle, we use quite a wide range of different kind of frequency RFID. We do corrosion detection under coating. This is a low frequency RFID and also high frequency RFID or even ultra high frequency RFID for different sensing application. One of the recent approach, we also try to use commercial off-the-shelf. So basically we can purchase RFID components on the market, and then this kind of the flexible RFID device, we can stick this one with steel material. Here, as you can see, we can have a different shape and steel with steel material. In this way, we can detect the coating condition, corrosion condition. We also can measurement the steel material property. In this way, we can get the digital mark for steel material. So this one, as you can see, we purchase this kind of RFID flexible device from the market. We just design electronic and they do the data acquisition remotely, and then of course depending on the communication distance, then we can get a different sensor information. We also can apply magnetic backhoe noise for stress measurement. So we develop one instrumentation system, use magnetic backhoe, just measurement the elastic or plastic deformation, measurement microcrack or microstructure, and then in this way we can measurement the steel material property. Because this is a typical electromagnetic probe approach here. So what we do different, we try to understand domain wall behavior, particular domain wall at the ground, inside the ground and the ground boundary, the behavior quite different. So to do that, so we use a vocal system to try to understand domain wall behavior. And then through this one, we notice the domain wall returning and the movement have a different kind of the time character. Then we use time character to understand, to do the measurement at the different stress level. So what we did, first of all, we changed the traditional way to design the Prof. We use not the simple, the yoke and the sensor system. We apply magnetic type head. So previously, probably some people can remember, we use this kind of tape head, can get a very tiny head reading area. In other words, we can get a high spatial resolution to measurement the stress, because stress actually also have the macro and the micro stress there. So in this way, we can improve spatial resolution, get the measurement right. Another one, we just use eddy current pipeline integrity for pipeline measurement. So this one we talk about operation and the maintenance. So I just show you, this one is a spin-up company. I think we working with China. And this one currently we already measurement globally around about 150 pipeline. What is the beautiful part? Because the eddy current pipeline can make the pipeline integrity much smaller. And this is the application there. So probably I show you the video. And the tradition where you use this one, just use a magnetic flux linkage, which is a book system and is very big. That's one for long distance pipeline is okay. But for branch pipe, the pipeline is small. For example, less than half meter. And then that's kind of diameter, so it's very difficult. Then we use eddy current. We can get a very good sensitivity and the pack system. So.
The benefit eddy current sensors offers higher sensitivity and signal to noise ratio. Can detect inline defects, including inner metal loss, abnormal welding, cracks, pinhole, deformation, and illegal taps, etc. Compact design and easy to deploy like cleaning bags. Can stand by non-standard, standard or temporary launchers. Value launching. Can pass 1.5D band.
So very 1.5 band, this kind of the portable system, so still can measure it.
Or 20% deformed headline. Can be driven by as low as 14.5 side pressure difference, with ideal running speed ranges from 0.1 meters per second to 8 meters per second. Suits for conductive headlines, including carbon steel, stainless steel, bimetallic composite headlines.
So we also can track in the pipe, the peak system, and then get the location information. And then after finishing the inspection, we can take the data out for decision making. Okay. Then I think we just show you about the non-destructive testing, use eddy current approach. We also can extend the eddy current approach with chipized system. So one approach, we use inductive digital converter. So this one, as you can see, the for pipeline, we have the different kind of electromagnetic sensor. I think later on, I think Carol Group and Dr. Zhou will talk about it a little more about their practice. One approach, we extend the eddy current, we just use resonance system. So basically we have the air inductance, we connect it to oscillator, and in this way we can digitize to do the work. This one is actually back quite a long time ago, 30 years ago, when I, as a young lecturer in China, I think we get the first patent and then do this kind of digitalization. So by coincidence, after 30 years, I think 2013, Texas Instruments actually developed this kind of the approach, use IC chips, they call LDC, digital inductance digital converter. So what recently we do, we just use this kind of chipless device, can develop displacement sensor. So basically measuring the gap between probe, between sensor and the steel sample, and also measuring the defect combined together. So in this way, we can get multiple function, but overall the approach just use one LDC devices to do the job. So this is the one application. Another one, rather than we use a magnetic sensor, we just also use an eddy current to hit in the sample, to measurement the thermography, to measurement the eddy current distribution for different application. For example, we can apply this one for high-speed railway to measurement the rolling contact fatigue of rail track. So finally, we just integrate different kind of approach to tackle the big problem, I think, for steel industry about the hard spot detection. Because the hard spot detection, I think, very simple, because this kind of defect or stress concentration is quite small. How can we do that? So again, we use, earlier we mentioned about use high spatial resolution probe, and get the sensor array, and to do different combination, we can use magnetic backpulse noise, we can combine with the eddy current, and then we can do different measurement, design different kind of sensor array for different application. So quickly, I just show you what we use different eddy current probe for different application, in not only sensing themselves, also include the communication, use wireless or power transfer communication. We also apply different kind of the magnetic principle. For example, include magnetic backpulse noise, use Doman wall turning, and also we extend the multiple function sensor, include use thermography and the resonance sensor for different kind of the measurement, defect, microstructure, and the stress measurement. So finally, I also would like to highlight here, I also in charge one journal, so hopefully this community can read or maybe can send your paper for non-destructive testing and evaluation. As you can see, this journal is small journal, but I think fast growing. I think this year we get impact factor 3.0. I think it's good progress in the last 2 years. Okay, and you can say our submission is keep rising. Thank you.
Thank you very much, Professor Tian. I think that we've seen here so many different ways in which the same kind of principle of sensors, the same underlying science can be applied really to give us much, much more information about the material. Now I'm going to pass over to Frank Zhou, who's going to talk a little bit about application of sensors in the steel processing plant and how that can be used to provide information to support optimization of materials processing. Frank.
Okay, good morning everyone. So my name is Frank Zhou, I'm from WMG University of Warwick. So it's really nice to hear the introduction by Claire talking about the importance of sensors for steel industry, and also see various different type of technique applied for steel product by Professor Tian. So in my talk, I'm going to focus on how we use smart sensors for microstructural control during steel processing. So I think Claire has really covered the introduction very well. The importance of the importance of the sensor is about making the steel products right as the first time. It's about we know more information about the product and enhance the quality control. So we know that the steel grade is achieved by engineering the microstructure of it. And in the steel mill, we're trying to adjust many different processing parameters in order to get the right property at the first time. And electromagnetic sensor is one type of sensor that we can put it in situ at a high temperature during the steel processing and have access of some microstructure information. So we know that there are a lot of link between steel microstructures and its magnetic property signals. So what I've got here is really a typical hysteresis curve of a ferromagnetic material. And we all know that majority of the steel, especially for structural steel and electrical steel, they are ferromagnetic. So they have these magnetic properties. So to start with, the steel will have a demagnetized state. So even though it's ferromagnetic, it has all sorts of this domain structure built into the structure of steel. So we have seen plenty of microstructures yesterday, but there are also domain structure. You have seen some of that in Tian's talk. So what happens is when you apply an external magnetic field, then the domain structure starts to move and the domains are starting to align with the external magnetic field. And of course, when the domain wall is moving for the domain alignment, the domain wall can interact with microstructure features. And this is why the microstructure and magnetic properties are linking to each other. So if we magnetize the sample fully at a very high field, achieve saturation, and then we just relieve the magnetic field, then the steel is actually coming back at a different point, which sometimes we have a piece of steel that is close to a magnet for a long time, then you have some remaining magnetism there, and we call that the remanence point. And in order to get back to zero field in the steel, we have to apply a reverse field to cancel that. So what I'm trying to show here is when you apply this magnetization process to a piece of steel, it undergoes quite a different various process of domain wall movement and domain arrangement. And if you record how the B and H, the magnetic properties, change during this magnetization process, you can then infer what is the microstructure of steel. So there are different techniques that applies different field strengths to look at steel microstructures. So at a cold environment, we have in situ cold rolling mill strength verification kind of sensors. So commercial sensors like 3MA, Harcom, and the IMPOC sensor, they all apply a very strong magnetic field, trying to magnetize very locally of the steel sample, and then measure the magnetic property at that point and correlate that directly to the mechanical property of steel. So it's very popularly used for link directly with things like tensile strengths, yield strengths, and starting to look at also R values. So it's a direct kind of empirical relationship there, looking at, because anything that strengthens the steel will also weaken the magnetic properties. So there's some correlation there. What we have researched at WMG Warwick is the online in situ sensor at high temperature. So here we're talking about a temperature range somewhere in between 800 down to maybe 400-500. So that's where normally the structural steel transformation is happening. So there we face the application challenge of electromagnetic sensor, that we can't place the sensor too close to the steel sample because of the high temperature. And also, the other difficulty is the steel strip or other shape of products will move at a continuous line, and that will introduce more noise to the sensor signal. So instead of using a very high field sensor, we are using a weak magnetic field sensor, and we then look at a very specific part of the sensor result and interpret what is the microstructure state at that time. So I love this diagram because it really shows the concept of how the sensor can work for microstructure monitoring. So two things can change the magnetic permeability of the steel. One is its microstructure, and the other one is temperature. So we know that there's a famous temperature called the Curie temperature, because above the Curie temperature, the steel lost its ferromagnetism. So everything is paramagnetic, and you see a very small signal from the sensor. However, passing the Curie point, if you have a steel product that has already transformed before this Curie point, which in steel is around 770, then imagine that during the cooling of that steel product, you will all of a sudden get a very strong signal at Curie point, because the material has already transformed. It should be ferromagnetic. It's just waiting for that temperature to achieve below the Curie. And as the sample gets cooled, you then see that we have a decrease in the signal, and that's simply because the permeability is decreasing with temperature. So that's if you have a fully transformed microstructure state. However, if you have a steel grade passing the Curie point and it hasn't transformed, then you start with a very low signal. So following the green curve, you can see that we have almost no signal at the Curie point. So we know that it's already passing the Curie, but there's no signal. It means the transformation hasn't taken place yet. And of course, during that austenite to ferrite transformation or to pearlite transformation, you will see an increase in the signal, because that's just the phase transformation is being picking up by the sensor. And after the fully transformed stage, you can see the signal then start to decrease with temperature. But what is even more interesting is you could have steel that can partially transform to ferrite. And let's say you just want 10% of ferrite or 20% of ferrite, and then you may be changing the cooling rate, or you just let it cool, and the chemistry of the steel means that a second peak could come out because it's a second transformation, because the remaining of the austenite can transform into things like pearlite, bainite, or martensite. So there we then have this electromagnetic response at a steel mill where the temperature measurement is very hard, because by enhancing cooling, you spray water onto steel plate, and you can have a very dust and wet and very difficult situation to measure accurately the temperature. So we have done a series of tests in the lab at WMG. So this is one of the equipments that we have, where we have a furnace and the run-out table. So this is really trying to simulate what is happening at the run-out table at a steel mill, where you have the hot rolling, and then steel comes out, and then you can decide to spray water on or forced air cooling for some of the rod product. So you control the cooling rates there. So what we are trying to do there is we heat the sample up to a certain temperature. We bring that sample out, and we actually stop at where the sensor is, and we can, to make sure the roller is still functioning, we sometimes move the sample forward and backwards, but the plate is still on top of the sensor, so that we can record how the sensor signal look like when a steel sample is cooled. And of course, in an industrial application, we can't do that, because the steel strip is running continuously passing the sensor. So you are having a snapshot of a temperature or a position, But if you have multiple sensor heads, that then record the transformation behavior. So we have got some samples here. I just want to show you some of the results that we have from the lab-based sensor, but the sensor is exactly the same as we have installed in industrial mill. So what I'm going to show you as a few examples is some mild steel with different thickness, and then a high carbon steel, and also a commercial steel plate. So if you look at the 3 mild steel sample, so they have very similar chemistry, which means that they should share the same CCT curve, etc. However, if you cool them, you will see that the transformation behavior is showing up on the sensor signal. So we have 3 different sample thickness, which are 3, 6, and 10 millimeter, and of course the cooling rate in air will be different. So what you can see from the sensor signal, if you look at a reading from the right-hand side where you have a high temperature, so this is sample coming out of the furnace, then not until the Curie point you see a sensor signal. At the Curie point, you can see that both the 6 mil and 10 mil sample have a sudden increase in the signal. That indicates some or a lot of the transformation has already taken place above the Curie point. And then upon cooling, you will see the signal start to drop with temperature. And the fact that they are at different height is just because the starting temperature of transformation is slightly different. And at high temperature, the permeability or the sensor signal is very sensitive to the temperature readings. But you can see that for the 3 mil sample, it actually transformed a bit later because of the higher cooling rate suppressed the transformation behavior. Now, we then think, okay, so that's what we measured from the sensor. How does that compare with dilatometry measurement, which is the standard measurement for phase transformation? So we weld the thermocouple on top of the sample, and we recorded the temperature profile. We then input that temperature profile into the dilatometer, and we want to see, do we predict the same transformation behavior? So you can see that the starting of the transformation for the 6 and 10 mil are very similar to what the dilatometry is predicting. However, for the 3 mil, we do see a difference between dilatometer and the sensor reading. And I think that there are a few different reasons. One is this specific cooling rate is very close to where the bainite or perlite transformation is. So any subtle difference in the cooling rate can produce that kind of difference in transformation behavior. But also what the sensor is measuring is not a single point. So it's not just a temperature at a single point. It's actually sampling a volume of steel sample. And of course, the temperature measurement we had is just the top of the sample surface. So there is some discrepancy there, but after we cut out the sample and look at the microstructure, we do see bainite transformation, and that tend to agree more with the sensor in this case. But it just shows that the sensor measurement, the model prediction, the dilatometry measurement can all measure phase transformation, but they have their own difference as well. So it's all different and giving different information. If we have 2 different steel chemistry, a high carbon and a low carbon steel, then you can see the response of the sensor signal will be quite different. One is because the low carbon steel tend to transform earlier, so that it transforms earlier means that it's at a high temperature, and the high temperature will result in high permeability and hence a high sensor signal. But also, different microstructure phase have different magnetic properties. So ferrite magnetic property is better, is higher than the perlite. So even though it's cooled down to a much lower temperature, you can still see the difference in the ferrite phase and the perlite phase for this example. So what if we have same sample and cool it at different rates? And this is just an example that we took a commercial plate sample and we try to apply air cooling and also water cooling. And as you can see, for the air cooling, we see something that is very similar to what we have seen in the mild steel. So the transformation from arsenide to ferrite has already taken place above the Curie. So you see this sudden signal increase and then start to decrease with temperature. And we see some slope change, which might be associated with the remaining arsenide to pearlite transformation. But if you use water cool, as you can see, you get a very different profile. The transformation is happening at a much lower temperature, around 430, and it's actually transforming from arsenide to martensite in this case. So I hope those examples give you a flavor of what the sensor signal actually look like, and when they are installed online in a steel mill, these are the type of signal we are going to get. So I think that's where we are, and I think the sensor technology that we have researched for many years now has been really lucky, and we have installed some sensors in Tata Steel in Moyden and now Tata Steel in Port Talbot. So one of the current thing that we are working on is to start gathering the sensor data from an industrial mill and read those sensor data, start to help us understanding the state of the microstructure of the steel product, but also starting to use those sensor signal to improve the mill model. And that will then enhance not only the current but also the future steel development and quality measurement online. So we have that one sensor hat sensor. It's commercialized by Primetal, and it's called EM-SPEC technology. And we have also now starting to look at applying the same sensor technology to different steel products. So within a catapult-funded project at WMG, we started to have multi-hat sensors. So at the moment, we have 4 hats in an array. So the reason of doing that is, one, we want to start to get spatial resolution across the width of the sample, so not just wide strip, but we're starting to install the sensors at Liberty narrow strip mill and start to look at narrow strip, so where the strip can move at different position, and that the 4 sensor hat can decide then which sensor hat is actually testing the center of the strip and which sensor hat information should we read from. But even more complex than that, we are also installing sensor at the British Steel rod mill, where you have a rod laying out on a round table like that, which is a really interesting geometry. But of course, that is a challenge on the sensor signal, because not only the microstructure and temperature is going to be affected, the volume, the density of the steel, as well as the position, the shape, will also affect the signal. So there, if we have multiple hats, we start to interrogate, to reverse engineer the data, and then trying to engineer the data into the pure microstructural information. The other benefit of having different, have a few sensor heads across the width in this situation is, as you can see, when the rod is coming out, the different density of the layout of the steel means that the cooling rate could be different at the center or near the edge of the webs. So different sensor heads can potentially pick up when do each different location start to transform, because you want to control the cooling rate so that the transformation is uniform in a rod application as well. So a lot of that is focused on phase transformation, and another area that we have done some feasibility in, and we also believe is a great sensor application area, is to apply the electromagnetic sensor technology for annealing application. So in this case, we have interstitial free grade, where we have the cold rolling followed by annealing, so where recovery and recrystallization is going to happen. So there we have also in situ measured the steel recovery and recrystallization process in a furnace where a steel sample is positioned within a sensor tube. But it's the starting point of thinking, can we also apply that sensor technology for the annealing process? Because the sensors seem to pick up the finish of the recovery, starting of the recrystallization, and the finish of the recrystallization. So that then is another milestone to control the microstructure during annealing. It's saving energy. When you achieve the desired microstructure, you don't have to anneal it further. So that's saving energy there and ensure the microstructure is the one that you want to get. The other application we tried this type of sensor is for rod steel. So this is the politic grade that deliberately we wanted the pearlite to fully spheroidized in this kind of fully precipitated microstructure. So there are heat treatment specially designed to achieve this microstructure, but currently the industrial partner is soaking the material for a period of time, but the sensor can potentially looking at how does the sensor signal change. In this case, we can see when the microstructure is changing from politic structure to fully spheroidized structure. The sensor signal is always changing until, in this case, about 11.3 hours. We then get this plateau of the signal, and we did interrupted test at a different stage of the annealing treatment to see what microstructure states they are, and actually they correlate very well with the EM signal. And when the 11.3 hour is reached, we actually already have a fully spheroidized microstructure there. So I hope I have given you a flavor of some of the electromagnetic sensor application for steel processing and its microstructural measurement, and some of the area that we start to look at as well. Thank you very much.